In the previous classes, we had discussed a property of an area that is known as the moment of inertia. We had seen the definition of the moment of inertia and how we use the definition to find out the moment of inertia of some simple shapes or any given curve. After that, we had seen the parallel axis theorem, and we had proven the parallel axis theorem, as well as we had seen some questions regarding the composite areas, how to find the area moment of inertia of the composite areas. Now, there is one more property of an area that needs to be discussed, and this is the module of the today's class. This another property of an area is known as the product of inertia. Okay, again, this is a property of an area just like the moment of inertia. And how it is defined, for that I have considered a lamina of some arbitrary shape. Okay, you can see that this is a lamina of some arbitrary shape, and suppose its area is equal to a. These are the reference x and y axes, and from this lamina I have considered a differential element, okay, a small element whose area is equal to dA. Suppose this is the centroid of this differential element, and from this centroid we are defining two distances. The first distance is the distance of this centroid of this differential element from the y-axis, and let us denote this distance by x, and also the distance of this differential element from the x-axis. Suppose this is denoted by y. Okay, so how we define the product of inertia? Let's define it for the differential element. So one thing we have to note, that product of inertia, it is always defined with respect to set of axes, not a particular axis. With respect to a set of axes. Okay, we know that moment of inertia was defined about a particular axis. We are saying what is the moment of inertia about x-axis, or moment of inertia about y-axis. What is the moment of inertia about centroidal axis? So whenever we were talking about the moment of inertia, we were saying that it is defined about a particular axis. But here the product of inertia is defined with respect to a set of axes. We can't say what is the product of inertia with respect to x-axis, nor we can say that what is the product of inertia with respect to y-axis. But it has to be defined with respect to a set of axes. Then I will say that what is the product of inertia with respect to xy set of axes. Okay, so if this is a differential element, I will say that the differential element has a product of inertia dixy. Now see here, xy is the subscript of this. Okay, therefore we always define the product of inertia with respect to set of axes. Okay, and for this differential element, what is the differential product of inertia? Is differential element का जो product of inertia होगा, that will be equal to the set of axes here is xy. Therefore the distance of the differential element from the x-axis and the y-axis, we have to take the product of these two distances. Okay, since I'm considering the set of xy axes, this reference axis, therefore for this differential element, what is the distance from the y-axis? That is equal to x, and what is the difference from the distance from the x-axis? That is equal to y. Their product multiplied by the area of this differential element. This will give us the product of inertia of this differential element about the set of axes xy. Okay, therefore it has always to be defined with respect to set of axes. Then this is the product of inertia of this differential element. Now to obtain the product of inertia of the complete lamina about the set of axes xy, we'll perform the integration. Therefore product of inertia of this complete lamina about the set of axes xy will be given by integral of the above equation. So this is the basic definition of the product of inertia. Okay, it is the mathematical representation of the product of inertia. So we have seen that it is defined with respect to set of axes, unlike the moment of inertia. Moment of inertia is defined about a particular axis. So this is one point of difference between the product of inertia and the moment of inertia, that moment of inertia is defined with respect to a particular axis. While as we have seen that product of inertia is defined with respect to a set of axes, okay? That's why for the product of moment of inertia, we will have either x, ix, or we have iy, or we have iz as well. But for the product of inertia, the subscript will be always containing two axes, that is x and y, okay? In 3D problems, it will be yz as well, xz as well. So limiting our discussion to the plane, therefore, we will use these set of axes, xy axes, okay? So this is the first difference between the product of inertia and the moment of inertia. So again, we can see that from this definition itself, we can again see that the SI unit is x and y has the unit of meter, and this differential area has a unit of meter square. Therefore, the SI unit is again meter to the power 4. Okay, and we can use other units as well. The other units will also include, depending upon the problem. SI unit is obviously meter to the power 4. Other units will be mm to the power 4 or feet to the power 4, whatever is given in the question. Okay, so this is the first point with respect to the product of inertia. Now let us look at one more difference between the product of inertia and the moment of inertia. If we look at the definition of the moment of inertia, suppose moment of inertia about x-axis is defined as y square dA. Okay, this y is a coordinate which has been measured with respect to some reference axis. Therefore, this distance y can be either positive or it can be negative. Okay, suppose this is the x-axis here. If the object is lying here, then this distance y is positive. And suppose if the object is lying here, this distance y here will be negative. Okay, but see here, since this y is squared, therefore, irrespective of the sign of y, whether it is positive or negative, this moment of inertia will always be positive. Okay, this moment of inertia will always be positive because we have a square with this y. Okay, the y can be positive or negative, but its square will always be positive. Therefore, moment of inertia is always positive. But the product of inertia can be positive, negative, or zero. Okay, it can have any value, whether it can have a positive value, negative value, or a zero value as well. Okay, so this is another point of difference between the product of inertia and the moment of inertia. Okay, product of inertia can be positive, negative, or zero, but moment of inertia will always be positive. Okay, so let's see one by one how it can be positive, negative, or zero. So for that, we can use the help of this image. Okay, so these are the set of axes, x-axis. This is the reference x-axis, and here this is again, and this will be the negative x-axis. Similarly, this is the positive y-axis, and this will be the direction of the negative y-axis. Okay, now take the example of this first quadrant. Okay, you can see that there will be quadrants formed: first quadrant, second quadrant, third quadrant, and this is the fourth quadrant. So if our object is lying in the first quadrant, see here, this is a rectangle, sorry, it's just a triangle, it is lying in the first quadrant. And from this triangle, if we consider this differential element, okay, now if I have to define, taking the example of the first quadrant, if I have to define the product of inertia with respect to ix y set of x's, then it will be equal to integral of xy dA. Okay, this is a differential element dA, and its distance from the y-axis is x, and from the x-axis it is y. Therefore, the product of inertia will be equal to integral of xy dA. Note that this distance x here is positive. Okay, you can see that this distance is positive because we are measuring it towards the positive x-axis. And similarly, this distance y is again positive. Okay, therefore both these distances are positive. Hence, we can say that the product of inertia of the object lying in the first quadrant will be positive. Okay, it will be positive because this is positive, this is also positive. Okay, now let's look in the second quadrant. If the same object is lying in the second quadrant, you can see that we can again take a differential element dA. Its distance from the this y-axis is x, but see here it is lying towards the negative x-axis. Okay, therefore this x is a negative distance. Okay, its sign will be negative because it is towards the negative x-axis, whereas this y will be positive. Okay, it's towards the positive y-axis. Therefore, if our object is lying in the second quadrant, we can say that ixy is again equal to integral of xy dA. But see, in this case, x is negative and this y is positive. Therefore, their multiplication will be a negative value. Hence, we can obtain that the product of inertia in this second quadrant will be negative. Okay, so we have seen that it can be positive. Okay, if it is lying in the first quadrant, it will be positive, and similarly, if it is lying in the second quadrant, it will be negative. Now, coming on to the third quadrant, students are now able to say, they will be able to identify whether in the third quadrant this product of inertia is positive or negative. We can see that this is the differential element. Its distance from the y-axis is x, but it is a negative distance. Okay, because it is lying towards the negative x-axis. Similarly, this distance y is negative distance because it is lying towards the negative y-axis. Therefore, in this case, this is negative, and their product will be positive. So moment of product of inertia in the third quadrant will be positive. And ixy, if we are talking about the fourth quadrant, one distance is negative, the x distance is positive, therefore their multiplication will be negative. Therefore, if an object is lying in the fourth quadrant, the product of inertia will be negative. Okay, so this is another point of difference between the this moment of inertia and the product of inertia. That is, product of inertia can be positive, negative, or zero. Okay, although we have seen here positive values and negative values, we are yet to see the zero value. It will be discussed shortly, but one must understand that moment of inertia is always positive, whereas product of inertia can be positive, negative, or zero. Okay, now what is the significance of the product of inertia? Although the significance won't be clear at this instant, and particularly for the civil and mechanical students, this topic will be discussed in detail in their upcoming semesters. Okay, because we limit our discussion here only to the definition of the product of inertia, but it actually helps us to determine, helps us in finding out the maximum and minimum value of maximum and minimum values of moment of inertia. which further helps us in designing the which helps us in designing the structural or structural or mechanical members such as beams, columns, shafts, etc. Okay, so let me take an example of this object. Suppose this is a cross section of a beam. Okay, it is in the rectangular cross section. There can be so many axes. Okay, let me take an example. This is one axis. This is one set of axes. There can be another set of axes which is inclined at some angle theta with this set of axes. So suppose this is x, this is y. Suppose this is x dash. Suppose this is x, this y dash. Okay, there can be another set of axes. Let me name that it is x double dash, and this is y double dash. Okay, there are so many set of axes, and this product of inertia helps us to find out that set of axes about which the moment of inertia will be maximum or minimum. Okay, this product of inertia helps us to find out uh, that axis about which the product this moment of inertia will be maximum or minimum, because those values of the moment of inertia, those maximum or minimum values of the moment of inertia helps us in designing the various mechanical and structural elements such as beams, columns, shafts. Okay, therefore it is necessary to find out and how can we use this. Okay, once we know the product of inertia, the product of inertia will be zero on some set of axes. Okay, it will be zero on some set of axes, on some set of axes. The product of inertia will be zero on some set of axes, and on that set of axes the moment of inertia is max or minimum. Okay, on those set of axes this moment of inertia can be maximum or minimum. Therefore it helps to identify the axes. Okay, it will actually help us in finding out the inclination of the axis where the product of inertia will be zero, and that axis on the product of inertia where the product of inertia is zero is known as the principal axis. Okay, although this detail is not necessary, just to brief about the significance. Okay, the principal axis product of inertia is zero, and on the principal axis if the product of inertia is zero, the value of the moment of inertia will be maximum on that product this on that axis, and hence it helps us to find out the product of inertia concept helps us to locate the principal axis where the product of inertia will be zero, and it is the location of the okay it gives us the orientation of the axis which about which the moment of inertia of the cross section will be maximum, and this further helps us in proper designing of the beams, columns, and shafts. Okay, although this will be further clear for the mechanical and civil engineering students in their upcoming semesters. Okay, so we have seen that moment of inertia can be positive, but product of inertia can be positive, negative, or zero. Now how is the product of inertia zero? Product of inertia can be zero as well. Okay, when it is zero, when any when at least one axis is the axis of symmetry. extremely important point that whenever at least one axis, okay, at least one, I mean to say whether x or y or both, okay, at least one axis is the axis of symmetry, then the product of inertia about that set of axes will be equal to 0. Okay, so there is no need that both the axes are symmetric. At least one should be symmetric, or both can also be symmetric, but at least if at least one axis is the axis of symmetry, then the product of inertia about that set of axes will be equal to 0. Now let's look at one of the schematic to understand this point better. See here, this is a lamina. Okay, this blue color shape is a lamina. It is a lamina. And here we have defined a two set of axes, that is the x-axis and the y-axis. Okay, here we can see that from the figure it is clear that this x-axis here is the axis of symmetry, because this x-axis is dividing the lamina into two equal parts. Okay, you can clearly see that it is the axis of symmetry, whereas this y-axis is not the axis of symmetry. Obviously it is not dividing the lamina into two equal parts, but x-axis is the axis of symmetry here. Okay, so see here, if I take a differential element dA, okay, I'm considering this differential element dA. Let me say that this is the first element dA. What will be its product of inertia with respect to the set of axes xy? So taking the first element, first dA element, the product of inertia of this element about this set of axes xy will be equal to its distance from the x-axis is y and the distance from the y-axis is x. Therefore, this will be xy dA. Okay, since both the distances are positive, x is positive, y is positive, therefore this value will be positive. Now, below this, okay, in the same line, but below the x-axis, we consider another differential element, dA, which is at the same distance of y. But the first element was, okay, it is at the same distance x from the y-axis. The distance for the element 1 and the element 2 is equal to x. Okay, first element and second element, these are both at the distance of x from the y-axis. And similarly, from the x-axis, the distances is same, that is y and y, but first element is above the x-axis and second element is below the y-axis. Therefore, this coordinate will be plus y and this coordinate will be minus y. So for the second differential element, this product of inertia will be equal to, we can see that the second element is again at a distance of x. Therefore, this is x. But see here, this will be written as minus y, because for the second element, the distance from the x-axis is downwards. Therefore, it has to be written as minus y. So we can see that this result will be equal to minus xy dA. So these two results are same, but their signs are opposite. Okay, same magnitude, opposite sign. If I add the product of inertia of these two differential elements, after adding, we can say that it will be xy dA minus xy dA. This will be equal to 0. Okay, so I have just considered two differential elements. There can be so many differential elements above and below the x-axis. Let me consider another differential element at some distance from the x-axis, and I will consider another differential element at the same distance from the x-axis, and their distances from the y-axis will be plus y and minus y. Again, if we add their product of inertia, okay, again if we add the product of inertia of these two elements, their addition will be equal to 0, because one will be having the positive value, and second will be, which is below the x-axis, it will also have the same magnitude, but it will have the negative value. Therefore, their net addition will be equal to 0. So many differential elements can be considered, and there I can consider another differential element here whose product of inertia is suppose I, and there can be another differential element below the x-axis whose product of inertia will be minus I. So summing up the products of inertia of all these differential elements above and below the y-axis, okay, the net product of inertia will be equal to 0. Okay, because there are so many differential elements and they have a corresponding differential element. Okay, if I take a differential element above the x-axis whose product of inertia is suppose I, corresponding in this differential element will have a corresponding differential element below the x-axis whose product of inertia is minus I. And when we sum up all these product of inertia, the net product of inertia will be 0. Okay, so when it is possible only when at least one of the axes is axis of symmetry. Okay, when at least one axis is the axis of symmetry. Okay, so whenever one axis is the axis of symmetry, the product of inertia will be 0. Okay, so I hope it is clear to the students. So based upon the concepts which we have learned, we can say whether the product of inertia about a particular set of axes is positive, negative, or 0. So let me take an example of a square. This blue colored lamina has a square. This is the y-axis, this is the x-axis. Okay, suppose the square has a side of a. Now the students can directly say that in this case the product of inertia will be positive because the square is lying in the first quadrant. It will be positive. Okay, it won't be 0, but it will be positive. Similarly, in this case, you can see that this is the reference x and y axis. You can see that the square is lying in the second quadrant. Okay, because if I take a differential element here, this distance will be negative distance, whereas this distance is positive distance, but their overall will be equal to 0. Okay, so this distance is positive, this is negative, therefore the overall product of inertia will be equal to, will have a negative value. Okay, it will have negative value, not 0 value. It will have a negative value because it is lying in the second quadrant. And in the both cases, you can see that no axis is the axis of symmetry. This y-axis isn't dividing the square into equal parts. This x-axis isn't dividing the square into equal parts. Okay, similarly in this case, this x and y-axis aren't the axis of symmetry because they are not dividing it into equal parts. Then the product of inertia won't be 0. Okay, it is only 0 when at least one axis, okay, is an axis of symmetry. So we have seen that in the first case it is positive and in the second case it is negative. Now looking at this figure here, this is x, this is y. Suppose this distance is a. Let me say that this is dividing, x is dividing into the square into two equal parts. This is a by 2, then this will also be a by 2 because the side of the square is a. Now, since this is a by 2, this is a by 2, we can see that x-axis is the axis of symmetry here. It is the axis of symmetry. So whenever one axis, okay, whenever one or both, but at least one axis should be the axis of symmetry here, we have I in this x-axis as the axis of symmetry. Therefore, we can definitely say that Ixy is equal to 0. Okay, Ixy is equal to 0. Now coming on to this figure, this is y, this is x. Okay, in this case, neither x nor y is the axis of symmetry. Okay, it is clear from the figure that these are not the axes of symmetry. Okay, so Ixy in this case won't be equal to 0. But it seems from the figure that Ixy will be having a negative value. Okay, from the rough analysis of the figure, this will definitely have some negative value. Okay, again, this is not necessary that only one axis is the axis of symmetry. If this is a square and if the reference set of axes is this is the center of the square. If this is the x-axis here, if this is the y-axis here, now both x and y are axes of symmetry for this square. So again, in this case, ixy will be equal to 0. We at least need one axis of symmetry, but here both axes are symmetry, axes of symmetry, therefore ixy still will be 0. Okay, thus ixy will still be equal to 0. So these points are quite important from the objective point of view. Okay, so what we have learned here today is the basic definition of the product of inertia and its difference from the moment of inertia. Okay, we have seen that product of inertia can be positive, negative, or 0. And we have also seen that product of inertia is always defined for a set of axes. Okay, that's why I always write xy axis. Okay, again, there is a parallel axis term for the product of inertia as well. Okay, parallel axis term for the product of inertia. Just like we had derived the parallel axis term for the moment of inertia, let's derive it for the product of inertia as well. Okay, so see here, I have considered a lamina of some arbitrary shape, and this lamina is having an area of A. Now I have defined a two set of axes. You can see that this x and this set of axes which has been shown in the green color is the axis set of axes about which I am interested in finding out this product of inertia. Okay, another set of axes has been defined by this red color. Let me say that this is x dash, this is y dash, and this point is the centroid. This point is the centroid. Therefore, x dash and y dash become the x dash, y dash is the centroidal set of axes. Okay, since this x dash is passing through the centroid and y dash is passing through the centroid, this is the centroidal set of axes. Okay, I want to find out the product of inertia about this set of axes, and this set of axes x and y, they are parallel to the centroidal set of axes. You can see that this x-axis is parallel to the centroidal x-axis, and this y-axis is parallel to the centroidal y-axis. Therefore, I need to find out the product of inertia about ixy. Okay, therefore I have to see what is the relation of ixy with ix dash y dash. Okay, that's the relation I'm going to derive. This is a differential element. Let me consider a differential element. Okay, this is a differential element dA. Okay, the complete lamina has an area of A, and this differential element has an area of dA. Let me denote some distances here. Suppose this is the distance of differential element from the centroidal y-axis, and let us denote this by x dash. This distance is the distance of the differential element from the x-axis, therefore let us denote it by y dash. There are two more distances that need to be defined. One is the distance between centroidal y-axis and that y-axis about which I'm interested in finding out the product of inertia. Okay, therefore the distance between these two axes can be denoted by dy, and the distance between these two axes can be denoted by dx. Okay, this is equal to dx. Now actually I'm interested in finding out the product of inertia of this lamina about this ixy set of axes. Okay, xy set of axes. Therefore, first of all, I will find the product of inertia of this differential element about the set of axes xy. Okay, so for this differential element, the product of inertia about xy set of axes, we know from the basic definition, it is equal to the distance of the differential element from the x-axis and from the y-axis. We can see that the distance of the element from the x-axis or y-axis here in this case, it will be equal to x dash plus dx. It is equal to x dash plus dx. This is the distance of a differential element from the y-axis, and what is the distance of the differential element from the x-axis? It is equal to y dash plus dy. Okay, this is the complete distance here. This is the complete distance here. Okay, so remember I have written xy set of x's, not x dash y dash set of x's. Then it would have been only x dash and y dash. Okay, so this is y dash plus dy multiplied by the area of the differential element. Okay, so this gives us the product of inertia of the differential element with respect to xy set of x's. Now to obtain the product of inertia of the complete lamina about the xy set of x's, that will be given by the integral of the above equation, that is x dash plus dx. In brackets we have y dash plus dy. We can perform some multiplication here. So x dash y dash plus x dash into dy plus y dash into dx plus dx dy multiplied by dA. Now this integral can be broken into four integrals. This is x dash y dash, and here we have dA plus integral of x dash dy dA plus integral of y dash dx dA plus integral of dx and dy and dA. Now, if we clearly look at the first integral, we can see that this first integral is actually the product of inertia of this differential element dA, but with respect to which set of axes? With respect to the centroidal set of axes x dash y dash. Okay, it is clear from the figure that this x dash, this integral, and that is integral of x dash y dash dA. It is the product of inertia about this centroidal set of axes. Okay, this is the product of inertia about the centroidal set of axes. Okay, so now let's look at the second integral. Second integral is integral of x dash dy dA. Now here dy is a distance, it is a constant. Okay, this is a constant. This dy is a particular distance, it can be taken out of the integral. Okay, this dy represents the distance between the x-axis and the x dash axis. Okay, it can be taken out of the integral. Now x dash dA. Okay, x dash dA, what does this represent? X dash dA represents the first moment of area. Okay, you can see that x dash is the distance between centroidal y-axis and the differential element dA. Therefore, this x dash dA here represents first moment of area about centroidal y-axis. And I had discussed this result in the previous class, that first moment of area about any centroidal axis, whether y-axis or x-axis, is always 0. This term will be 0, okay, because it is the first moment of area about the centroidal y-axis. Now similarly, we have another integral, that is y dash dx dA. This is the third integral. Now this dx is the distance between two axes, that is a constant, it can be taken out of the integral y dash dA. Now what does y dash dA represent? See, y dash is the distance of the differential element from the centroidal x-axis, okay? Therefore, y dash dA represents the first moment of the area about centroidal x-axis. So this term here is actually the first moment of area about centroidal x-axis, and this should also be equal to 0. First moment of area about any centroidal axis is equal to 0. Okay, so this is the third integral. Now the fourth integral is equal to dx dy dA. Dx and dy are two constant distances between the axes, therefore they can be taken out of the integral. And this total integral, this integral is what? Integral of dA is the total area of the lamina, therefore this becomes a dx dy. Okay, this becomes a dx and dy. Now the previous term, which was comprising of the four integrals, is just reduced to two terms, because two integrals, okay, second integral and third integral are 0. Therefore, what happens to our equation? The first integral is equal to this, second was 0, third was 0, and the fourth integral was equal to this. This is the mathematical statement of mathematical representation of parallel axis term for product of inertia. And what does this say? Okay, we can interpret the result. Product of inertia about a set of axes xy, which is parallel to the set of axes x dash y dash brackets. In brackets, we can say that this is the centroidal set of axes. Okay, product of inertia about a set of axes xy, which is parallel to the centroidal set of axes x dash y dash, is equal to the product of inertia of the area about centroidal set of axes plus the product of area and the distances between the axes. Okay, you can see that the product of inertia about any set of axes xy, which is parallel to the centroidal set of axes x dash y dash, is equal to the product of inertia about the centroidal set of axes plus, okay, plus the product of what? Area and the distances between the two axes. Okay, so this is complete discussion regarding the parallel axis term for the product of inertia. Now there is a one problem given in the book. It tells us to find the product of inertia of this right angle triangle about the set of axes, that is xy. Okay, for this figure I have to find the product of inertia, but about the set of axes xy. Okay, so what is the basic procedure here? We can take a differential element. Okay, we can take a differential element. This will be our differential element. It can be either horizontal or vertical, and this differential element will have a centroid here. Okay, this will have a centroid here. So at the distance of x, I have taken a differential element whose thickness is equal to dx, and the height of this differential element is equal to y. Suppose the height of this differential element is equal to y. Therefore, its centroid will lie at this distance of the centroid will be y by 2, because this differential element is in the shape of a rectangle, okay, whose centroid will be at half of the distance. Okay, since this differential element has the length of y and thickness dx, therefore its area will be equal to y dx. Okay, before knowing about this, before proceeding in this question, we also need to find out the equation of this line. That is, we need to find out that what is the function of y with respect to x. Okay, you can see that this line is a straight line. Its equation will be y is equal to mx plus c, and you can see that there is no y-intercept, therefore this c will be equal to 0. Therefore y is equal to mx, where m is the slope of this line, that is given by tan theta. So if this is theta here, the slope will be equal to perpendicular upon hypotenuse, therefore it will be equal to, sorry, perpendicular upon base. Tan theta is perpendicular upon base, therefore h by b will be, this is the b distance, that is the base of the right angle triangle, into x. Okay, so this is the y as a function of x. This is the equation of this straight line. Okay, this is the equation of this straight line. So we have taken the differential element. For this differential element, the product of inertia about xy set of axes will be equal to the distance of this element, the distance of this differential element from which axis? Y axis, that is equal to x multiplied by the distance of this differential element from the x-axis. Now see here, when I'm taking the distance of this differential element from the y-axis, I need to take the distance of this centroid of the differential element from the y-axis. Okay, because different points will have different distances from the y-axis, therefore we take the distance of the centroid of the differential element from the x-axis. Therefore this will be equal to y by 2, and this is dA. So it will be equal to 1 by 2 xy. dA here is equal to y dx. So this will be equal to xy square by 2, okay, xy square by 2 dx. So the difference, this integration is to be performed with respect to x, therefore it is mandatory to write y in terms of x, and y in terms of x is given by h by bx. Therefore dxy will be given by x by 2 y square. Y square means h square by b square and x square. We have a dx here as well. So this will finally be equal to h square by 2b, h square by 2b square x cube dx. Now the total product of inertia will be given by performing the integration. These constants can be taken out of the integral. and we are left with integration of x cube with respect to dx, and x varies from 0 to b. Okay, this is x equal to 0, this is x equal to b. The limits of the integration will be from 0 to b. Therefore, it will be equal to h square by 2b, 2b square here, x raised power, okay, it is equal to x raised power 4 divided by 4. And the limits from 0 to b. So ixy will be equal to h square by 8b square, and we are giving the upper limit that is equal to b. After simplification, this will be equal to b square h square by 8. So this is the product of inertia of the given right angular triangle about this set of axes I, this xy set of axes. Okay.